Okay, you probably notice if you are continuing from the preceding video that I've kind of wiped out a lot of the picture on this side of the z-axis. Okay, and the reason is that r is strictly non-negative. Okay, that our r for the whole region is going to go from 0 to 4. So we think in terms of partitioning the r interval from 0 to 4 and ask ourselves, if we take a typical point inside of that partition, what are the limits on z? Well, actually there are two answers here, because we really have to break this question or break this description into two regions. If we're between here and here, then in a typical partition, r is just going to go from, and let me use a little different partition because I'm going to interfere with something I had up here. Okay, if this is our partition, okay, and then we have some r star within the partition and draw the vertical segment through that value of r star, we see that z goes from whatever this value is to whatever this value is, okay, over here. And we have nothing in between to interfere. In other words, z goes all the way from here to here, and we stay inside of our spherical shell. And that's going to be true for any r between 2 and 4. But if r is less than 2, then we have the problem that we have to go a ways before we encounter our region, the spherical shell. Okay, this part is empty. There's no spherical shell here, so our z values start here and end here. And they also start down here and end here. Okay, so we have two different ways. We have to describe this in terms of a split region. And that should be no surprise to you. You've done this with regions in the plane, so it's no different for regions in space. If we don't have just one way of describing our region, well, we have to split our definition. So between 2 and 4, between r equals 2 and 4, that's between here and here. And of course, for any theta between 0 and 2 pi, our z value goes from the square root of 16 minus r squared, negative square root of 16 minus r squared, to the square root of 16 minus r squared, for the same reasons we had over here. I don't want to clutter the picture up, but obviously I can construct a triangle from the origin to this point. The radius, or the hypotenuse of that triangle, will be the radius of our outer circle, which is 4. And our distance from here to here is r star, whatever r star happens to be for this particular subinterval of our partition. Okay, so we have a here, we have r star here, and a equals 4, so we have 4 here and r star here. So 4 squared plus the magnitude of our z squared is going to have to equal 16, 4 squared. R star squared plus the z coordinate squared is going to have to equal 16. And as a result, the z coordinate is going to be, well, at this point, z is going to equal 16 minus r star squared, and here z equals not 16 minus the square root of 16 minus. And it's going to be here the square root of 16 minus r star squared. So that whatever r star happens to be at this point, z is going to go from negative square root of 16 minus r star squared to 16 minus r star squared. Or if r is the distance from this point to this point, then it would just be r squared. Okay. This describes the part of our sphere that lies more than 2 or more units from the z-axis. Now you wonder why I don't have anything on this side of the sphere. Well, this picture corresponds to some theta between, let's say, could correspond to theta between 0 and pi. And then so we rotate around from 0 to pi, we get this picture. Rotating from pi to 2 pi, the r-axis could be thought of as reversing, and we'd have this half. But the bottom line is that it's the interval from r equals 2 to 4 that's being partitioned, and theta goes from 0 to 2 pi. And if we rotate this interval of the partition around the z-axis from angle theta equals 0 to theta 2 pi, we get the entire cylindrical shell in this case. Between radius 2 and radius 4, an entire cylindrical shell, an infinite cylindrical shell, parallel with the central axis at the z-axis. Radius, inner radius being 2, outer radius being 4. And then when we restrict it by this set of inequalities, we constrain ourselves to be within the sphere. So now we've got a description of the part of the sphere that lies 2 or more units from the z-axis. Okay, now, for r between 0 and 2, though, we have a lower limit on z. Z goes from, well, what's z here? This is a sphere of radius 2. If we do our triangle the same as we did here, it's like our radius is a, but it should be clear if we construct a triangle, radius 2, hypotenuse 2 from here to here, distance r from here to here, that the z-coordinate is going to have to be the square root of 4 minus r squared. Up here, square root of 16 minus r squared. Similarly, so we get the top half of the region between r equals 0 and r equals 2 within this spherical shell. That gives us the top half going from this to this. So we have this region. We also have the bottom half. And what happens in the bottom half? Well, c is going to be greater than or equal to negative square root of 16 minus r squared, and less than or equal to negative square root of 4 minus r squared. So really we need 3 regions to do this. Okay, somebody observed, well, couldn't you use symmetry and just say that, well, this is going to be the same as this, so just do this integral and double it? Well, yeah, depending on what we, well, yeah, maybe, depending on what it is we're trying to find. If we're just trying to find the volume, then that'll work just fine, because the volume of what you have between z equals 0 and 2 above the coordinate plane, the r theta coordinate plane, and the volume of what you have below are the same. If you have a density that's symmetric with respect to the r theta plane, you could still do it, and you could integrate the mass and find the same thing. If you have a density function, for example, that's not symmetric, then you're going to have to do both of these integrals, because this one won't end up equaling this one. Or if you're integrating to find something else. If you're trying to find a moment of inertia about the about the z-axis, you'd be fine, because the moment of inertia of this part here above the coordinate r theta plane is going to have the same moment of inertia as this part below. Again, assuming a density function that's symmetric with respect to the r theta plane. Okay, so you could have that, but let's say just you have a constant density, everything's nice and symmetric, but you want to find the moment of inertia about the line z equals -1. Well, you'd still be okay just finding this integral and doubling it if you have a constant density. If you wanted to find the moment of inertia, though, about a line parallel to the r theta plane but not in the r theta plane, then you would no longer have the symmetry and you wouldn't be able to do that. So you just have to make a careful judgment about your symmetry. So if you're tempted to just do this part and double it, be sure that what you would get down here would in fact be equal to what you would get up here. we can then write down our integral. Okay, if we're just integrating volume, now I'm just going to indicate the triple integral, and instead of the r dr d theta dz volume increment, well, I can write that out. dv equals r dr d theta dz. So if we wanted to find the volume, we could take the triple integral from r equals 0 to r equals 2, and from theta equals 0 to 2 pi, and from what? From z equals negative square root of 16 minus r squared to the square root of 16 minus r squared. Now our dv would be, again, in this case, we would use, first thing we'd integrate with respect to is z, so it would be dz, and then d theta dr, and of course we'd have our r there. So to match the order of these variables with the order of the description, we would have to use this. But then it would have to be plus, and we could do 2 times the integral, and I'm not going to have a lot of room to write the z limit, so I'm going to make that integral sign smaller. Okay, we would go from 4 minus r squared, square root of 4 minus r squared, to the square root of 16 minus r squared dv, where again our dv is going to be r dz d theta dr. And of course then we're going to go from r equals 2 to r equals 4, and theta from 0 to 2 pi. Now that's written a little small, but hopefully this will give you some perspective on the questions we've got to answer and how we can represent spheres, at least, in cylindrical coordinates, spheres and spherical shells if we need to.